Hello everyone, my name is Monika, and today I'll present our recent work on open vocabulary semantic segmentation, which we call clip DIY. Let me start with a short introduction to the task of open vocabulary semantic segmentation. Given an input image and a free-form textual prompt, the goal is to produce a segmentation mask for given prompts. Precisely, we classify each pixel that corresponds to any of the given prompts, and on the contrary, we put all the unclassified pixels to the background. As we can see, the main difference between open vocabulary and classic semantic segmentation is the nature of semantic classes, which in our case are not predefined and can take any form. With clip DIY, we managed to achieve good results on the task without any additional training nor pixel annotations. In general, densifying clip is a non-trivial task and multiple methods attempt this problem. Our method is the first to leverage clip as it was designed, so for image classification. It also leverages an unsupervised saliency detector. We achieve state-of-the-art results on PASCAL VOC, and our method performs pretty well in the wild. So how does it work? Given an input image, we first encode an image in a sliding window fashion, which we do at multiple scales, meaning we first get a full image, and at the next scale, we cut it into four partitions. And we can perform the same operation even further, more granular. Then we fit the partitions to a clip image encoder and obtain clip representations for all of them. Then, given input textual prompts, we encode them using clip text encoder and obtain the respective vector representations. Having text and image representations in the same space, we can now get the similarities between all the image partitions and the prompts in a classic clip.product fashion. After merging and upsampling to the original resolution, we arrive at the per-scale map of text similarities. Finally, we obtain our dense clip map by simply averaging all the output maps at different scales. However, as we can see on the example, our produced semantic mask is still not fully accurate as our partitioning mechanism lacks the objectness information about the shapes. Therefore, we refine the extracted map with objectness guiding mechanism. We fit an image to an unsupervised foreground background segmentation method found and extract the saliency map. Finally, we refine the predicted dense clip map from the previous step with an information about the background from the saliency detector. Precisely, we put non-salient regions to the background. For more details, I advise to have a look on our paper. Here I'm going to share just a little bit of technical details. So we resize input images to the size of 256 to 256 pixels, and we found that the best results our method achieves using three different scales. As we can see on the example on the left, we can recover full shape of the bird when using scales from 0 to 2. At the scale 3, we can still segment some parts, whereas at the scale 4, the partitions are simply too small for meaningful classifications. Let me share some results. So when it comes to quantitative results, clip DIY outperforms all the other methods on PASCAL VOC by a large margin, and it achieves good results on COCO object with just a 1 point of MIOU dropped compared to the state-of-the-art ClipPy. Qualitatively, our method produces high-quality masks on both compared datasets. Our method works well even in challenging scenes, such as the one in the middle, with elephants hidden by the trees. What is more, you can really prompt very different concepts and still obtain good segmentation masks, as shown here with our in the wild examples. Our method is capable of segmenting different types of dishes from different cuisines. It also produces masks when describing different types of materials and colors. It can also be useful when segmenting particular monuments, like these two famous buildings in Paris. And finally, Clip DIY can even find Nemo. To summarize, I presented an open vocabulary semantic segmentation method, which is unsupervised and training-free. It uses clip and saliency detector funct, achieves state-of-the-art results, and performs well in the wild. For more details, I encourage you to have a look on our paper once again, and thank you for your attention. Of course, our code is available. You can see it under the following link, and I'm happy to take any questions at the conference in person or virtually. Thank you.